Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet to be published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the last episode of this year's series of webinars with academics of the ITU Journal on Future in Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open the webinar today with Professor Jeffrey Andrews from the University of Texas at Austin. We count on your support to make this webinar an exciting experience. Please submit your questions via the Q&A channel. We will address them to our speakers during the Q&A session. After the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live life lessons. So please stay online. Professor Andrews agreed to a personal chat. He will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm pleased now to introduce Professor Ian Akilditz, the editor-in-chief of the ITU Journal and founder of Truva. 3 years ago, with Professor Akilditz, we launched this new scientific journal, and we are now moving towards impact factor. Professor Akilditz is Ken Byers Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. In the last 2 decades, he established many research centers worldwide, including South Africa, Spain, Saudi Arabia, and Finland. He is editor-in-chief emeritus of impact factor journals, highly cited and at the top of the most prestigious international rankings. Ian is visiting distinguished professor in several universities around the world. His current research interests are in 6G, 7G wireless communication systems, hologram communication, terahertz, molecular communication, Internet of Bio-Nanothings, and many other subjects. So I'm pleased to give the floor to Professor Akilditz to introduce the speaker and moderate the Q&A session. Ian, the floor is yours.
Thank you, Alessia. Good morning, good afternoon, and good evening worldwide from Abu Dhabi with love. I again welcome you all to the 4th season of our ITU Journal for Future and Evolving Technologies webinar series. In the first 2 seasons, we had the research leaders from the academia, where we had the leaders from the industry in the 3rd season. We are fortunate to have the top scientists lined up in this season. Before I present our speaker, Professor Jeffrey Andrews, I would like to briefly talk about our journal, ITU Journal and Future and Evolving Technologies, in short form, FET or FET. The objective of our journal is to bring the academic and industrial worlds together in order to establish a strong bridge between the academia and industry. Our journal ideas were incubated back in December 2019, and the inaugural issue came out in December 2020. It is an open access journal, no fees for the readers, no fees for the authors. The papers go through a review process, and we try to cover all forefront research activities in the world, both in the academia and industry. I would encourage you all to submit your papers, and also if you have ideas for special issues, please do not hesitate to contact us. At this point, I would like to thank Cesar Onoe-san, Bilal Jamusi, Erika Campagnola, and in particular, Alessia Magliarditi for their infinite support for this journal. Today, I have the great pleasure and honor to present you our today's speaker, Professor Jeffrey Andrews. First of all, I must personally thank Jeff for taking time from his very busy schedule and accepting our invitation to deliver this distinguished seminar. I met Jeff more than 15 years ago. I always follow his outstanding research. And before going through his biography in detail, I must mention some preamble opinion. In my opinion, Jeff is one of the top scientists currently in our field, and he made many research contributions in all wireless communications the last 15 plus years. A stellar career so far, and we expect that he will continue his outstanding contributions. He contributed many pioneering results in wireless communication that the list is long to cover here. His total number of citations is 110,000, and his H index is 110. And currently, Professor Andrews is the Trutchard Family Endowed Chair Professor in Engineering at the University of Texas at Austin, which is one of the top universities, as you all know, where he is also director of the 6G at UT Austin, or UT. He received his BS in engineering with high distinction from Harvey Mudd College and MS and PhD in electrical engineering from Stanford University. Andrews is an IEEE fellow and ISI highly cited researcher and has been co-recipient of 15 Best Paper Awards, including 2016 IEEE Communications Society Information Theory Society Joint Paper Award, 2014 IEEE Stephen O. Rice Prize, 2014 and 2018 IEEE Leonard G. Abraham Prize, 2011 and 2016 IEEE Heinrich Hertz Prize, and 2010 IEEE ComSec Best Tutorial Paper Award. And his other major awards include the 2015 Terman Award, NSF Career Award, 2020 Gordon Lepley Memorial Teaching Award, 2021 IEEE ComSec Joe Low Cicero Service Award. Rest in peace, Joe. He was a very nice fellow and good friend of mine from University of Illinois at Chicago. And Illinois Institute of Technology, as I can recall, a long time ago. IEEE ComSec Wireless Communications Technical Committee Recognition Award, and 2019 IEEE Kiyo Tomiyasu Technical Field Award. He graduated many PhD students, and they're all successful. Some of them have like 5 of them are already IEEE fellows, several professors at top universities in the USA, Asia, and Europe, and industry leaders on LTE and 5G systems on which they collectively hold over 2,000 US patents. I again welcome Professor Andrews to our webinar and wish you all an enjoyable and productive time listening to his talk entitled Unlocking New Capacity in 6G Cellular Systems via Site-Specific Machine Learning Aided Design. Again, thanks, Jeff. The stage is yours.
Well, thanks, Ian. I think you've raised the expectations very high with that extremely generous introduction. So I will do my best here. Let's see, let's try to get this. Hopefully this is looking proper now and everyone can see my slides in presentation mode. Give me just maybe a thumbs up, Ian, if that looks okay. Or, okay. So yeah, well, thank you for tuning in, both of those of you who are live or watching this later. And the point of this talk is to give a bit of an introduction to some exciting research areas that my group has been doing, and I've also been following other people's work, and just to give a few opinions and perhaps look to the future for 6G. So what I'll talk about today is a very short preamble on how I see machine learning fitting into wireless. Obviously, much has been written about this, a lot of people working on this. I'll just give a few thoughts, both at the beginning and end. And then most of the talk will be on 3 specific things we've been working on with in my group. the last few years, which I think hold some promise and have a common theme in that they really are about using machine learning to optimize to an unprecedented level various techniques in a cellular system where you can do things this way that you couldn't do without a machine learning based approach. So I'll talk about that through 3 examples, and hopefully these examples will be just different, but also have this common thread that you'll identify. Okay, so first of all, just want to talk about, just a few questions on machine learning. So as I said, machine learning is obviously filtering into almost every field, not even just technology fields, but education and law and everything else. And so wireless is no different, but wireless is somewhat unique in several respects, in that these systems have been very carefully engineered over decades by very smart people. And there's, in many cases, really strong theory underlying the way we do things today. And so first question, there's questions of, all the questions you could ask about wireless at a high level. First is, where should we do it? And so, you could do this in various places. I have it broken into 3. So you can do it on the actual end device, like the phone or whatever the end device is. And certainly Qualcomm and other companies that, Apple and so on, Google, are looking at doing this. And things that, happen on the phone obviously need to be very power efficient. You can't do a lot of training of these things. They need to be, almost invisible to the network side. So, but, this is a, figure taken from Qualcomm, and they are certainly putting like small GPU and other neural net cores into their chips. So we'll see an ever-growing capability of the phone side itself. And the second thing I'll talk about today does assume that the phone can do a small model type machine learning algorithm. Now you can do things at the network edge, meaning the base station or things like the base station in an O-RAN architecture. And this is going to unleash a lot of new players into the ecosystem. And I think this is where a lot of the exciting machine learning aspects can happen in wireless that are wireless specific, things at the edge. So things will have to run fast there. They need to be scalable. You need to be able to deploy them all over the network, obviously, and so they can train independently. And this will be the theme of my work today. Most of the things will be in the second category that are being done at the network edge. Now, you can also do things in the cloud. This will be the third category of things. In my third contribution, we'll talk about things that would be mostly done in the cloud. And this, things would not be real time, so they would not affect things on the communication time scale, which is on the order of milliseconds or perhaps tens of milliseconds. But you could do very sophisticated things back in the cloud. Indeed, I see a lot of training of models as well as data generation and data processing, network management. These things could happen in the cloud. And you have companies like NVIDIA that are very much betting strongly on this. Being a major aspect of telecom in the 6G era. Now, why and how and should we do machine learning? So why should we do this? Our systems, like 5G, kind of work. They work pretty well. So what do we need machine learning for? Well, they could work a lot better, for one thing. But I think this is this why question is really in the process of being answered, and I think this is where particularly students and researchers really can help answer this question. I mean, even NVIDIA, one of the most powerful machine learning companies in the world, is trying to answer this question and looking to academia to help answer it by finding use cases where it can really do something that's non-incrementally better than what is done today by existing algorithms. And also, how to do ML is important. There's a gazillion different flavors of machine learning that run the gamut, from very fancy high high complexity models that take tons of data to train, to very lightweight things. There's time series type approaches like reinforcement learning, or other more static approaches. And it's for wireless, because these are such complicated systems with so much complexity, and and they need to work, right? If they stop working or you don't understand what they did, this can be a big problem. So how do take these from sort of a research domain where they show some promise into prime time, meaning deployment, and to ensure robustness and be able to identify what's going on in the network and when to revert to safe modes, meaning like how we do it today, are also really important questions for getting these into the 6G cellular network. And then finally, something I thought a lot about is, what do we need to do in the standards themselves to support machine learning? And I'm not really sure about this. We could, I think all three things I present today could be done without really almost any standard support, very, very minuscule changes to the standards, if any, which is interesting. I think, one interesting thing about wireless systems is they already are endowed with a great deal of measurement capability, a great deal of feedback from all the devices to the network. This happens today, irrespective of machine learning. Every phone's constantly telling the network things about its channel quality, its channel dimensionality, its what the channels look like, its SINR. So you can actually do quite a bit with what's already there. This, I think, is an open question. The standards are certainly looking at this, but I think the more that we can do without explicit standardization, the better. Okay, so out of all the different types of machine learning aspects, the thing I'm going to focus on today and tie together is what I call site-specific machine learning aided design, or site-specific artificial intelligence. And what I mean by site-specific is that today when you deploy base stations, for example, in the network, they have a ton of different parameters that you can set and different ways that you can do things. And they do some adaptation. Some of it is in real time. Some of it might be over time. They try to figure out things like how to configure the array. It's very manual. It's very ad hoc and heuristic, and it's not very scalable, and it generally doesn't work that well. So what I'll show today is some examples where we could do a lot better. And there's other examples in the literature. This is just a small sampling, but I think in a broad sense, one of the areas I think machine learning can really improve on how we do things in wireless systems today is by enabling a generic network to be deployed, but then each base station or each cell site configures itself to be optimal or close to optimal for that environment. And that environment includes things like the propagation environment, so what the structure of the environment is, as well as where the phones or the end users tend to congregate and what they tend to do in that cell. So all this can be learned in principle. And if you learn it, there's ways to communicate much more efficiently. And that's what we'll show today and through these three examples. Okay, so the first example, to get a bit concrete, this is one that I've done with my student Ethan, who just graduated, and so I'll show you how this works. We've been recently collaborating on extending this with Ahmed El-Atib, who's at ASU, Arizona State University, and we collaborated on this with Samsung throughout the project that we were doing. So. I assume most of the audience knows a bit about millimeter wave communication. That is, one of the key new pillars of 5G, and what promises really transformational higher data rates. And so far, it's not been that easy to deploy. They have relatively short range. Propagation is a real problem as far as diffraction and penetration, and then you also have to put these in all the devices. And so, this is going to be a 10 or 20 year project to really get this upper spectrum really working well and achieving what it can possibly achieve in 5G and 6G. But the basic idea in 5G is how you align these beams is essentially a trial and an exhaustive search type approach. And it's you could perhaps call it a hierarchical search, but basically what happens is the base station sends out broad beams with a high spreading factor, and what I'm showing here, and then eventually it identifies for each UE which broad beam was the best for it, and then it sends narrow beams within that broad beam to try to narrow it down, and then eventually after this process, it identifies the best beam to that UE, and the UE is also trying to simultaneously identify its best beam forming vector back to the base station. And this has to be done for every UE. So this refinement phase is on a per UE basis, takes a lot of time because they have to actually cycle through all the UEs, UEs meaning the user equipments, the phones. And so it's slow, consumes a lot of power, and it's one of the main bottlenecks to getting this working. And if you want to go to even higher frequencies in 6G, like terahertz or above 100 gigahertz, this is even harder because the beams have to be narrow. So it's a huge bottleneck, big problem. Okay, so we'd like to have improve upon this, in a major way. And the thing is, we want to try to there's lots of approaches that have been proposed for this. This is a known problem. Lots of research has been done on it, but you need to have all of these properties for it to really be good. I mean, after all, the reason they're doing this exhaustive search in 5G is because it does reliably find all the UEs in the cell, and you have to do something that can find all of them. You can't just like do a compressed sensing approach for a single one of them, or do this on a pure UE basis. Okay, so these are the properties we want to have. I won't just read them, but we'll try to achieve all of these with what I show you today. So our method follows the 5G approach in that we have a potentially a two-stage process. We can also try to eliminate the second stage. We send out wide beams over the whole cell. So the goal is to find all the UEs, but rather than sending out generic wide beams like what's done in 5G today, where it just kind of covers the angular space with these wide beams, instead you learn a new way to send these quote unquote wide beams that is particularly suited to the cell site. So we call this the probing codebook, and this is learned, and this is site specific. So every base station would learn, things like, for example, it's unproductive to send energy in this direction because nobody ever seems to be in this beam, and we're going to send it in this other direction. Heuristically, that's what's happening, but we'll do this with a much more principled approach. Okay, so we'll find a optimal probing codebook. There'll be a small number of beams that are sent out, often. So every 10 milliseconds, 100 milliseconds on this order, and then all 100 milliseconds roughly, that all the UEs try to listen to. Then we have a second stage, a second neural network at the base station that then uses feedback on these probing beams from the UEs. So this is just how it works in 5G today. The UEs listen to those, send feedback on the signal strength of each of them. And then we have another neural network that will synthesize a beam to that user, either directly or through a codebook-based approach where there could be a refinement phase. All right, so we'll look at two different approaches there, both the codebook-based one, which at that point is essentially, it's a classification problem. You're trying to classify from the feedback what the optimal narrow beam is. And so that's a bit of an easier machine learning problem. And then the second one is what we call the grid-free, where you're directly synthesizing an arbitrary complex valued beam. And so this is in a continuous action space, and so it's harder machine learning problem from a training point of view. So that's how it works. I've listed how it works here, so I won't read the slide. But just to show, for the codebook based approach, it's really fairly simple. There's a few layers here. It's just a standard fully connected multi-layer perceptron, very simple, old school neural network architecture, nothing too complicated. What's I think important about this is, so we train this using channel realizations, which have to be gotten somehow. I'll talk more about that later. But we train together these two neural networks, the first being the probing beams, which then we kind of extract this W after the training process. And these would be what we would actually send out every 100 milliseconds or whenever we send out these synchronization signals. And then we jointly train it with the beam selection neural network. So what's cool about this, and in this case, it's with a cross entropy loss to try to identify the best beam of that codebook. And for the arbitrary beam forming vector, it's a similar approach, but the architecture is a bit more complicated. You have to have various normalizations and things, and conversion between amplitude phase and real and imaginary. But the basic idea is the same. And the key idea is that you're not training these probing beams to maximize SNR or anything like that. You're just training them such that they maximize the probability downstream of predicting the optimal narrow beam. And this is important because we think part of the reason our technique is really excelling, and we'll show this later, is that it's picking probing beams that give an optimal input when the UEs feed back on them into the like a spatial signature that allows you to predict a narrow beam, and that's the key aspect. Okay, so for all the results I'll show you today, we're getting H from a ray tracing data, but this can be done in a variety of other ways as well, and is indeed an important aspect for any practical deployment. Oh yeah, so I okay, so let me just very briefly talk about the how we tested this. So we have 4 different sets of data. They're all based on the wireless Insight ray tracing tool at the current time. We're doing research actually right now to use a very high fidelity simulator for this. But this is, it's commercial grade ray tracing software that's commercially available for this part. And so we used some of Ahmed Al-Atib's data that he released, as well as one we created ourselves from the Washington, D.C. area. And it's kind of standard 5G type parameters for millimeter wave. We're looking both at outdoor as well as possibly indoor approaches for this. And we'll see they all perform actually very well. I'll just show here the 28 gigahertz outdoor probing beam. So just to show kind of what they look like. So this above here is for a line of sight scenario with just 6 beams here or 8 beams here. So again, these are the ones sent every epoch to all over the whole cell. And so what you can see in the line of sight scenario, this is just for like 100, like a 120 degree type sector. They span the whole area as you'd expect for like line of sight channels, but it doesn't just break it up like the current 5G beams do into sectors, smaller sectors, but rather it sends some energy in terms of like little lobes. Like say this purple beam here is all one beam. It sends out sharp little lobes that kind of collectively cover the space. And we think it does this because this allows the UE then to feed back non-trivial, a set of received values on each of these beams, so that you can help pinpoint where the UE is and what would be an optimal narrow beam to that UE. Now, in the non-line of sight, the scenario, we have a blocking object kind of in the middle, and the probing codebook learns to avoid that and instead reflect energy off of buildings over here on the sides to get behind it. So it kind of passes the smell test that is learning to do something that reaches most of the UEs in the network. Okay. You can also do this same sort of scenario on the UE side. We call this a sensing codebook, but this because each UE will have a different position and rotation in the cell, we would consider these to be like generic for all UEs. So this receiver side codebook is not so important. Any reasonable set of beams will do equally well. Okay, so just quickly to show some results that for this data set. So what we see is if we do an exhaustive search, you have the green line. And so as you expect, the more searches you do, the higher the SNR you have. So like this, the more searches here is to the left. And so like the time of searching is to the right. So faster to the right is better. And but if you do more searches, you get higher SNR. What we see is our approaches, which are the blue and orange lines for just the single stage search where we immediately synthesize a beam, are about 2 orders of magnitude faster for a given SNR than just the current 5G method. So that's a really dramatic speed up. Now this is done for a few different data sets, lots of UE positions in the cell. So this would be, we think it's not it is something that could be recreated in practice. So you can just, with just a very small number of total searches without a refinement phase, really reliably synthesize a narrow beam. So this is we think very promising approach. We just did a recent further extension of this. We did a new data set in Boston and tried to unify some of our results with Ahmed Al-Atib's, and we found that indeed, we have we're finding similar type results, even implementing them all together. And the main thing is that we see there is a really significant gain from doing the site-specific probing beams. Even if you did a machine learning like type prediction on the generic beams, you get a really like a 10x or more speed up. And this is just for the transmitter side from doing this site-specific approach. So we think this is a very promising approach for how to do beam alignment going forward and using machine learning. So the main, I think, I list some future directions here. And I think, these are, research academic type results, but, we have tried to make them as realistic as possible, but we need a lot more experimentation. We're currently working with NVIDIA we're going to be some of the, I think we'll be the first academic group to use their new super high fidelity simulator. It's called Aerial Sim, and it does, you know, massive ray tracing over like an entire city, and you can do multiple cells, many UEs, mobility, higher 5G stack. So we're in the process of trying to prove this out with them, because they also think this is a very promising use case for machine learning. So hopefully we'll have some results on that in the next 6 months, to show, you know, in something very closely approximating a real system, how you could do this. And then how you would actually train this for a real system. You have a couple options. You could use something like Aerial Sim, NVIDIA's tool. They're planning to make it so they can do this for every city, like in North America, for example, and eventually the world, where they would have a digital twin running in the cloud, and you could train things like this on it. That's one option in a few years from now. It sounds crazy, but you could actually do an offline optimization of every base station in a provider's network, and then deploy with those parameters. But you still have to do some updates, and these can be done by, you know, harnessing all the feedback you're getting continually from the UEs in normal operation. So I think very interesting to see how this could get implemented. You know, I have a list a few other extensions here, you know, that, you know, would have to be considered to go to you know, a real world implementation. Okay, so I think this is a promising use case for machine learning. Now let me give a I don't know if I should take any questions now, if there are any on this specific.
Please continue, Jeffrey.
Okay, great. Okay, so the second example, and this is very recent work. We haven't actually published or even submitted this for publication yet. We'll probably submit the paper in the next week. And this is on looking at one of the main bands that's being looked at for the 6G era is kind of an intermediate band between the lower bands that are currently very widely deployed for both LTE and 5G, and then the millimeter wave bands that I was just talking about. So because the millimeter wave bands have been hard to deploy and, you know, and expensive to deploy, there's a lot of interest in looking at some other intermediate band where for 6G, where you could get a bunch of bandwidth, like on the order of 1 or 2 gigahertz of bandwidth, but hopefully have some propagation that would allow a less dense deployment. So this is a study that we've undertaken with Nokia on this spectrum, in particular on how to do MIMO in this spectrum. And so, you know, I just kind of mentioned this as far as this trade-off. You know, you could, you know, get this high capacity because of the amount of spectrum, but also, you know, we expect the channels here to offer some scattering and more richness than higher frequency channels that would allow, you know, considerable MIMO, multi-user MIMO to be done. You know, the antenna arrays will be large, but not nearly as large as millimeter wave. So idea is that you could do quite a bit more digital beamforming in these in this spectrum. And so we're trying to, you know, we know a lot about how to do MIMO optimally, but one of the really hard things in this sort of regime where you have so many antennas, you know, maybe on the order of 256 at the base station, maybe 16 at the UE, is estimating this channel is really challenging, you know, for all the different UEs and in all the different subbands. And so you want to do this with as little explicit pilot tones or feedback as possible. And so that's what we're kind of looking at here. So the basic architecture is we'll have a neural network, a large neural network at the base station that's attempting to learn from UE feedback directly how to do pre-coding to those UEs. So the basic idea is that it's this closed loop system, this end-to-end deep learning system, where the UEs have a small neural network where they are listening to, you know, in the real system, how it would work is they're listening to downlink pilots broadcast from the base station to estimate a channel, that estimate their downlink channel, which is, you know, a bit smaller dimensional. Well, I mean, they have, you know, smaller received array, so it's easier for them to then estimate. They attempt to then compress this from the pilots into some uplink signal that they send back through the same channel, since we're assuming a reciprocal TDD band here, to the base stations. The base station would get this collection of uplink feedback signals from the UEs, and then from that directly try to do an implicit channel estimation and pre-coding. So that's the setup here. So it's kind of putting deep learning at the heart of how we would do MIMO. We're assuming, for the purposes of this talk, that this is narrowband. So this means we're using OFDM or some similar type of approach for handling the multipath and the intersymbol interference. But can we do a lot of the MIMO processing with neural networks? And the nice thing here is we have really good baselines because we know what's optimum, from information theory. And there's been some recent work also on kind of in a similar vein from Wei Yu's group and some others in Korea, looking at how to do a high dimensional multi-user MIMO system with feedback and pre-coding. But ours is quite different in the sense that we are doing TDD and also with multiple antennas at the UE, which really makes the problem actually much harder than with a single antenna, because it's a full MIMO channel to each UE. Okay, so just to show kind of, start with a very simple result. So, if we had single user MIMO in this regime with just 2 data streams going over this channel, we're using ray tracing data mostly here from that Nokia has produced. And we're trying to do this with, not too many pilots. So here, just 2 main pilot symbols, pilot like matrix. By symbols, I mean a whole vector of symbols across the antennas. And so, we have a true upper bound, which would be, if we know the true channel, we could do a singular value decomposition with water filling. And so that gives us a true upper bound. And we can see our proposed method gets close to that. You could also get close to that with using an MMSE type channel estimate followed by a SVD beamforming. And if you do, sort of an orthogonal pilot matrix, rather than trying to do an optimal pilot symbols that are sort of genie-aided by knowing the true channel, you have a little gap here, but it's not too bad if a few dB. Where our technique really shines, even in this simple single user case, is where if you only send an insufficient number of pilots back to the base station. So rather than sending the 2 you need for a rank 2 channel, you just send 1. So here the MMSE channel estimate won't do so well. And so you have quite a bit of a gap when you do the SVD based on it. And so what our technique still hugs pretty close to the baseline. It's able to somehow do a projection based on because it's not doing an explicit channel estimation. It's just implicitly using the compressed pilot symbols by the UE side to determine the downlink precoder. It can still track quite close to the upper bound, which is interesting. Now, if you did this with instead just a statistical channel, the same thing doesn't hold, and that makes sense because what's happening here and why we're able to get so close is that we're learning the environment of the cell. So this is the kind of site-specific aspect. There's ray tracing. The ray tracing uses the structure of the cell, and so you're able to learn this structure eventually in the neural net. And so when you see even just a sparse amount of pilots, you're able to have a much better idea of what the channel was. But if you go to a statistical channel, which is stochastic, and so there's not really any structure to learn, then there's not much gain from doing learning in that case. So that's, I think it's intuitive, but we observed that. Now, if we move on to multi-user MIMO, which is the mechanism where we'll really get major capacity in these mid bands, because you can send to multiple users simultaneously, even if they each individually have low rank channels. So here we're sending 2 streams to each user, and the first observation we make is if we just extend our technique that I just showed you to multi-user MIMO with feed-forward neural networks, it does okay. It's able to do better than matched filtering, which is just optimizing, just matching to the channel, which is like beamforming, but it's pretty far away from block diagonalization, which is not quite the optimum, but it's the more or less the this is block diagonalization with the true channel. So it's very close to, it's basically essentially the achievable optimum that doesn't use a really crazy precoder like dirty paper coding or successive interference cancellation. Okay, so there's a bit of a gap here. So the question is, how can we close this gap? And what we realized was that you need to have some mechanism for the precoder to learn a channel inversion. So what block diagonalization is doing is, it's a per user channel inversion essentially that's then orthogonalizing the users. And the feed forward neural net on its own is not capable of learning this inverse structure. So if you have a trainable inverse structure that can learn weights, then this really is the ticket. And so this kind of shows that to do machine learning in wireless, you need to understand the theory, you need to understand what optimal structures are likely to look like. And then if you put those structures in, then you can learn the weights that you need that are tuned to that specific environment. So in that case, then we do get very close to the upper bound with our approach. And there's quite a bit of a gap to not without a learnable pseudo inverse type structure, or with kind of the just a normal channel estimate followed by block diagonalization. Again, has quite a big gap. That's the green curve down here. So deep learning does seem like a good approach. Again, you need to have some reason to do the deep learning, and here the reason is that you don't want to send pilots to fully learn the channel, but you can learn enough about the channel from from the historical data that if with a deep learning approach, you don't need as much pilot information instantaneously all the time. You just can have a little bit of information, and then the neural network sort of stores the overall structure. Okay, and this is why people are looking at for big MIMO channels. There's a variety of ways that people have proposed to do channel estimation more efficiently than linear methods. Okay, so the last thing I'm going to talk about today. So the second one, we'll have a journal paper with more results coming out in the next week or two. We'll put on archive. So if you're curious about that, please look for that. And the last one is shift gears pretty to a kind of a different approach. This is we're going to be more above the physical layer, and we're going to look at a whole network. And specifically, we're looking at, say, a deployment in a city. And how do we optimize the overall base station parameters throughout the whole city so that they work together very well? Okay, and this is done with AT&T labs. So I know you're in Europe. So AT&T is the largest, or one of the two largest providers of cellular service in the United States, and one of the largest in the world. And their labs happen to be in Austin, which is great. So we can collaborate with them so easily. So we used their in-house tools to help with this work, and they'll explain a bit more about it. So, and we have some recent papers on this, and we're still working on some additional things I'll give a preview of today. So what I'll mainly talk about today is a very simple problem, very simple to understand, but very hard to solve. Okay, so the problem is, each base station, that's deployed in a cellular network, you have these antenna panels, and then you have to figure out how to have all the antenna elements on them. And this is just, you can think of this just for a CISO situation, just for sectorization. You have these sectors in the antennas, and you want them to cover a certain amount of space, both angularly in the vertical and the horizontal direction. How wide do you want the sector to be? And then how vertically compressed do you want it to be? The more vertically compressed it is, the more antenna gain you get, but then of course you lose, some dynamic range, as far as covering a wider range in the vertical direction. And then you also have down tilt, which is, how the physical direction that this sector is pointed in. And these three things actually have a very large effect on the coverage region of the cell, and where, the signal string throughout the cell. Okay, so I've shown this with this angle. And so what you'd like to do is deploy, what makes this really tricky is that how you deploy this in a given sector then affects the interference in all the neighboring sectors, specifically, the nearby cell sites. And so what you'd like to do is maximize some function of both the downlink SNRs and the uplink SNRs in your cell, and in fact over the entire network. So you want to optimize, this function could be, so how this optimization problem we'll look at both the downlink and the uplink. And this is actually new. Existing work mostly just looks at downlink optimization. We'll show that it's important to look at both. And then we'll look at optimizing two things simultaneously. One will be coverage, which we quantify as, the fraction of users above a SINR threshold. That's just what this little math shows here, as well as the logarithm of the sum rate, or rather the sum of the logarithm of the rate. And the reason we do this is this kind of a fairer metric rather than, you don't want to maximize sum rate. This will just bias you to like really maximizing the rate of the nearby users rather than the edge users. So this is like a fair cell-wide fairness type metric. And we'll see it does well over the whole distribution of SINR, not just the ones that maximize sum rate. Okay, so this is what we want to do. Now, why is this still a research problem in 2023? The reason is you can't actually solve this problem. It's non-convex, it's combinatoric. Even for a moderate sized network like 20 cells, you can't. It's like an infinite number of settings you could have for all these different angles and degrees. Even if you quantize it, just you can't even do an exhaustive search. So how people do it now, like in 3GPP, they run a exhaustive search over a moderately sized network where they constrain every base station to have the exact same setting, which is obviously not optimal. And then they find the best one where they all have the same setting, and then that's the suggested default settings. So that's what we use as our baseline today, is the cellular industry's suggested settings. And then because these settings aren't that great, there's a lot of hand tuning. So when operators deploy these, they hand tune them. They're like, oh, this is not working very well. We hand tune it. That affects the neighbor. It's a huge problem. It doesn't work at all well. And this is something really ripe for a data-driven approach. Okay. We tried a bunch of different things, actually. When I first saw this problem, I'm like, oh, this is, a reinforcement learning problem. Each base station is an agent. They take feedback from the users. They see what happened. They take some new action. They observe what happened. They explore the space. This doesn't work well for a few reasons. One, it's really unstable because what you're doing in one cell affects the other cells. And at least for us, we could not get the reinforcement learning algorithms to converge to a good solution. It was very unstable. We tried various multi-agent reinforcement learning approaches. We talked to reinforcement learning agent faculty and experts. Anyway, so we scratched that after a while. Could still be a good thing to look at in the future. And we tried a few different things, Bayesian optimization and so on. And we settled on this approach, which I'll just really briefly summarize. It's like a Bayesian optimization combined with a genetic algorithm for evolving known decent settings to other possibly good settings. Okay, so it's just an optimization algorithm for essentially predicting what good settings will be, so we don't have to try everything, because we can't try everything. It's too many settings. So it kind of harnesses the best of both Bayesian optimization using this Gaussian process regression, as well as this genetic algorithm for trying to mutate and then pick possibly good new settings to try. And then we have so this model then kind of essentially weeds out what might be good settings, and then we actually test what we think might be good settings on AT&T's network-wide simulator. So this is their in-house simulator. Took many engineers years to develop, something we could never have developed in an academic setting. And so we use their 5G simulator. It simulates a large network, all the aspects of the stack, all the aspects of the network. It's what they actually use for their own tuning. And it takes an hour to run 10 milliseconds of actual network simulation. So that's why we have to be judicious on which, even for the simulation, we have to be judicious on which setting, how many settings we try to use. And so this kind of, very, very cool that we were able to use this. It's, for us, about as close to a real network as we could ever hope to have access to, to be able to do this kind of experimentation. Okay, so this is a picture of one of the scenarios we looked at, where this is just a snapshot of macrocells and small cells, and of UEs. The UEs can be dropped in, randomly, and we averages over many different UE drops for this network. And we have some baselines here. We also collaborated with Facebook and Ryan Drefhurst and Robert Heath. They've been working on this with both Bayesian optimization as well as a reinforcement learning approach. Now they can only do that for a very small network, because for reasons I'll explain, because this is basically the reason. as you get to a larger network, the Bayesian optimization has a cubic complexity with each iteration because it stores all the previous history and does like a matrix inversion, which is cubic. That's at a high level why it's cubic. Whereas our approach has linear time complexity, does not increase with time. It's exactly linear. Okay, so as far as actual performance, this just shows the downlink. You can see that it's quite a large improvement over the 3GPP baseline or the Bayesian optimization, that took so long, and the improvements over the entire distribution, from edge users down here to even the best users, and especially the median users. They all get a few dB gain from this. Now, we also show that it's really important to do both uplink and downlink jointly, and which is not typically done. They typically just look at downlink, and this is actually a really bad because the uplink winds up often being the coverage limiting direction in the network because the UE doesn't have a lot of transmit power, and we show massive increase of like 10 dB in coverage here. Versus just doing a downlink only optimization. In the uplink, it's terrible. You lose a huge amount if you just do a downlink optimization. Whereas if you do them both jointly, you only lose a very, very small amount from the joint optimization in each direction. So even if you just perfectly optimize the uplink or the downlink, doing it jointly, you just have a very small degradation in each direction. So it's like you get the best of both worlds from a joint optimization. So that's, I think, one important finding in this work. Some recent work we've been undertaking, we've been extending this to like more complex scenarios with where we can actually change which direction we point the sectors in, not just the shape of the beams, but the direction of the beams. Also trying to do load balancing to force traffic onto small cells or millimeter wave cells. And also a thing we've been looking at is how to protect radars. So for example, in these mid bands I talked about earlier, the 7 to 15 gigahertz, or even in the upper C bands, there's radars existing, U.S. military radars, other military radars, and you need to, you can learn where those are without too much trouble because they're transmitting out radar signals, but then you need to protect them. So you can actually harness this exact same framework to protect a known incumbent. So like here a radar. So we show, how you could, so we now not only want to optimize coverage and capacity to our users, but also minimize interference cost to some military radar, say, that's on a tower somewhere. Okay, and we show that this really works well, so we can still get improve our capacity here is the middle plot, decrease our outage, so we get almost the same type of behavior without considering the radar, and we can lower the radar interference by about 20 dB, which is a huge amount in doing so. That's, I think it's again, this is just kind of a proof of concept, but we actually presented this. This was presented to the upper brass at AT&T because this is a big problem. They need to be able to promise to the U.S. government that they're not going to knock out these military radars if they deploy cellular networks in the spectrum. And so this is one technique that can be used to really, attempt to accomplish that. Okay, so I'll just have a few parting remarks before we go to Q&A, and these are just sort of observations. I really switched from doing mostly theory, stochastic geometry and information theory type research about 6 years ago to doing machine learning. Just kind of wanted to do something new and learn more about these tools. And so there's just a few things that we've observed from our own research and from others is, as far as doing things at the link level, it is quite interesting that you can take out all these things that we've been learning since Shannon and working on, and you can throw neural networks in there instead. And if you train them right, they can do about as well. It's very interesting, but it's not I don't think anyone's going to do that because the way we have like things like modulation, coding, OFDM, these have been not only optimized in theory and are very close to optimum, if from a pure theoretical level on a link layer, it's very hard to beat what we're doing currently, at all, period. And then also on an implementation level, companies like Qualcomm and the base station vendors, they have this down to like a science, these are squeezed into tiny little cores that consume like consume almost no power. So ripping these out and doing it with machine learning, people are talking about that, but I just don't see that happening. Okay, where I think machine learning will really be powerful is the stuff I'm showing today, where you have a system level approach where you don't know what's optimum, like the last one, or you can't do what's optimum. Like in the beam alignment case, it just takes forever to find the optimum beam, or it requires a ton of channel estimation, where you'd be sending almost entirely pilot symbols to do optimal. So this is where I think we can really get a gain from a data-driven approach. And the basic idea is, rather than doing things from scratch like they're done really in 5G today, almost every 10 milliseconds, you almost completely start over. Instead, you build up knowledge of what's happening, and then so you can make decisions that are adapted in a much more comprehensive way. And that's where the gains I've shown today are from. One thing I thought is interesting is, from theoretical research back in when most a lot of wireless ideas can be advanced with theory, you'd have some cute idea, you'd show the theoretical gain from it, maybe it's 3x, and then you simulate it, maybe it's 2x, and then you go to implement a real system, and you hope it's even like a 20% gain. And in machine learning, it's actually the opposite. So the more realistic you make the scenario, the more gain you'll see from a machine learning technique. So we saw that, for example, doing like an IID Rayleigh channel, which is great for theory. It's proving theory. It's useless for machine learning because there's nothing to learn. You need that structure, you need that complexity, and that's where machine learning can really get in there and do things that provide non-incremental gains. So this means that for future next 10 years, 20 years of wireless, we need to work with really high quality simulators, high fidelity simulators. That means likely working even more closely with industry to test out our ideas, because this will not only make them more practical, but also that's how you show the gains. You show the gains by having these high fidelity systems that where there's a lot of gap between a simple approach and a sophisticated approach. Also, I think it's encouraging in that a lot of the things we can do don't require really heavy ML. They can be done at the network edge. Returning to the beginning of the talk, they can be done at the UE. We'll still do stuff in the cloud. We can use heavy machine learning things like large language models or transformers, deep generative models for maybe data synthesis, generation, fault detection, things like this. But for the real-time stuff that's being done constantly at the network edge and on the UE, these can be pretty simple. So they don't need to burn a lot of power or be really hard to train necessarily. So that's it. That's all I have today. So I'm happy to take any questions.
Thanks a lot, Jeff. Excellent talk. There are many questions, and I will start to read them to you. You can also see, but there is no order, by the way. So first, Ruben is asking, in the example 1, what is the time scale at which the machine learning algorithm learns the directions in which to do the exhaustive search?
Great question, Ruben. Yeah, so I assume what you mean here is the probing beams that we're sending out, to the whole cell, periodically. And so the time scale we're imagining is quite slow. So we're, the simplest case, you could just learn a single set of probing beams, and that would be averaged over all the UE locations in the cell. So it could be over days. And you would then, because the main goal of these probing beams is just to cover the places that UEs tend to be, and with more energy, and to avoid places where they aren't. So you avoid blocking objects, you avoid lakes, you avoid things like that. And so this doesn't have to be done on a very fast time scale. So I think that's very important. You could consider having a couple of different settings. You could have like a morning setting, an afternoon setting, if the UE distributions are different, and you'd get some gain that way. But for our baseline case, we think this could be done with just even a single set, single averaged over all the day, and even over weeks. So very slow time scale is the idea.
Also, Ruben is asking in example 3, are there any tunable parameters that you need to set to trade-off between optimizing the uplink and downlink?
Yeah, I mean, we're tuning the exact same parameters. Actually, I have a longer version of this talk where we give some examples of like uplink settings and downlink settings and how the joint ones differ. But unfortunately, it's not super explainable. We don't know. We did have a parameter here that sets the importance between the uplink and downlink, which we just set to 1/2, but you could set it to more to value the downlink or the uplink more. So we had that. It was a settable parameter. We're not exactly sure why what it's doing that's so different than a downlink optimization, but there seems to be some very important differences between the joint optimization and just a downlink only or uplink only.
And there is also a question by Pedram. He's asking, did evolutionary algorithms used in cellular networks so far in practice? If yes, for what applications and how they handle the time-consuming aspect of the algorithm?
Yeah, good question. I actually don't know the answer to this question. Unfortunately, companies don't tell us what algorithms they're using. So there's certainly nothing in the standards that has evolutionary type approach. Whether any companies using it, I don't know, unfortunately. But I don't know of any example.
And there is an interesting question. I mean, it's not a question, but he creates a scenario. Pavel Kulakovsky, he says about beam alignment problem. I had similar questions in the classrooms, really. Anyhow, why don't we use the following very simple approach? Let the MIMO array at the base station to measure the transmittance of the training signal coming from the user in the uplink channel. Then let us use the complex conjugate coefficients maximum ratio combining approach for the signal transmitted to the user in the downlink channel and have a perfect beam forming. Is this just because we have FTD everywhere?
Yeah, good question. Yeah, no, we have TDD. Let's assume TDD. Let's assume reciprocity. But the problem is that the UE doesn't. It's like a chicken and an egg problem. So because of each of these antenna elements at the base station is so small, and at the UE is so small, if the UE just sends a pilot, it has to send a beamformed pilot, and it doesn't even know which direction to send it in. So if it got lucky and it sent it toward the base station, then the base station could listen to this. That's true, and then beamform. If it was able to do an estimate, it could then beamform back into the same direction. But there's insufficient gain on the UE side to do that with any reliability at all. So that's why you have to do this probing approach, where you send down a lightly beamformed signal, and you do it with a lot of spreading gain. I didn't mention that very much, but that's also important for these wide beams. They can't even hear these wide beams because they're too faint. They can only hear them because they then accumulate them over multiple symbols. So they use like a ZF2 sequence or a similar type orthogonal sequence that's long, and then you accumulate that, and then you have enough energy to give a reading. So that's the reason, is that it's a chicken and egg problem. You can't actually even hear each other until you have some beam alignment.
Thank you, Jeff. There is another question by Amir Shohail, or Shuhal. Digital twin simulation with NVIDIA will be first of its kind of testing.
Okay, so to the extent I understand the question, I think it will be more or less the first of its kind. Now, I don't know what every other company's doing. I know Qualcomm and others are working on very high fidelity simulators, but NVIDIA's vision is that they'll have, they haven't released this yet to the public, but they'll have this essentially digital twin of a wireless network that will run in the cloud with, a kind of unthinkable amount of, complexity today, but it'll run in near real time when they have it all tuned and optimized and running on their big GPU servers. So that is the idea, and I think my students and I are kind of the guinea pig right now, working with them and their engineers to try to kick the wheels on this from an academic point of view. I think they're also working with a few companies, select companies, on this. Like the Nokias or the Ericssons. I know they're working with Ericsson on this, but yeah, so we're kind of trying to do an academic proof of concept of our beam alignment approach with them.
There is also a question. This is a broad question, by the way, from Amir. He's asking about the 6G core versus the 5G core, and please go ahead. Before I say something. Okay, go ahead.
Yeah, unfortunately, I'm not much of a core expert network. Obviously, there is a lot of evolution going on in the core, but I'm not the right person to answer that.
I can maybe.
Okay, good. But Ian probably knows more than me.
Definitely 6G core will be similar to 5G. It will be heavily based on SDN, software-defined networking, and network function virtualization, and much more usage of automatic network slicing techniques. So these are the major issues, and then plus you will have these cell-free massive MIMO technologies heavily used also in 6G and on the RAN side. So core is, as I told you, it will be heavily based on SDN and FE. So I have another question. I think I covered all the other questions from outside. So, you presented your results mostly for the lower frequency bands, mostly like for 5G. And so when we go to the 6G, as you know, that we will be talking about sub-terahertz and even, hopefully terahertz bands. And so can we use your solutions ideas straightforward, or there will be new challenges when we go to higher frequency bands?
Yeah, well, I mean, everything's going to be harder, in those bands as far as, the beam alignment problem, right? Because you need, much bigger arrays, even more directional beams. So I think, I don't see any reason my first contribution couldn't be scaled up to that scenario. I think the need will be even greater at the terahertz bands because the beam alignment problem will be even harder. So I think
because there will be very single pencil sharp beams, so it will be very, very challenging, right?
Yeah, so I think you'll need something like the first contribution. I don't know. I don't think my second, the latter two ones I talked about would be very applicable to above 100 gigahertz.
Okay. So thank you, Jeff. And I assume there are no other questions here. Oh, Ruben again jumped in. He cannot let it go.
No, it's a good question, actually. So this is a common question. So let me answer Ruben's question. It's basically on the time scale and on mobility. And the way for the beam alignment one, the way it should work is that you should train it over so many UE positions that mobility doesn't matter. So if a UE moves, they're still just in another position that you've already trained the probing beams for, so that they would just have different feedback on the same probing beams. So you don't need to adapt this on the timescale of mobility at all, right? If you had to do that, it wouldn't work.
I don't know that the other participants can read the Q&A here. The question from Ruben was about the example one again. The time scale can be slow, or as I understand, the algorithm is primarily learning the geometry of the environment around it. Is the same approach applicable for faster time scale adaptation? For example, for an environment with moving objects that influence the optimal beam search directions. And again, he thanks to Jeff for the insightful talk. So Jeff answered that, right? So there are no more questions. And I greatly appreciate your great talk and also the running the Q&A session very smoothly. Thanks a lot, Jeff, again. And I ask my colleague, Alessia, to take over and ask you life lesson questions. Thank you, Jeff. See you.
All right, so now for the hard questions.
Thank you so much, Ian, for moderating this session. And thank you, Professor Andrews, for your very insightful talk. So now it's time to move to the Wisdom Corner, live life lessons, which is based upon the idea to give a unique and special angle to this series of webinars, adding a personal touch. So I would start with my first question. Which is your hard-earned life lessons or failure that you would like to share with us today that might perhaps be helpful for someone attending this webinar?
Wow. Just so everyone knows, I did not get these questions ahead of time. So these are all spontaneous. Yeah. Well, I think if I just really think about that, I guess I never really saw myself winding up in this position, to be honest, as a professor at a top university where people would care about my research. I think at each stage of my student career, I felt it was a struggle. And I had to kind of, in many stages, even going back to when I was a teenager, find like a new level by, usually by, working hard or, finding a mentor who could help me, understand how to study better or learn better. And, really just learning how to focus my energy and my concentration. I think that's one of the hardest things we all face. And me, certainly to this day, even, is just my biggest barrier is my own lack of ability to focus and concentrate. So many distractions in life. And so I think, and even more so now than when I was a child. So I guess for the folks here, I would say just learn something that works for you, that allows you to focus and concentrate and get away from the busyness and clutter and distractions of the world. And that's what I think I was able to do at several different stages of my career, where honestly I thought I wasn't going to do very well in college. I almost thought I was going to fail out, and then I wound up being top of my class. I got to Stanford. I'm like, everyone here is so smart. How am I ever going to get into a do well? And my first year was very tough, and I got hammered by all the on all the exams, and then I wound up getting straight A's my last 4 years and doing a good PhD. And so I think I guess just that sort of perseverance and resilience and not giving up is something I think has served me well, and it'll give me now when things are really hard. I just kind of have that belief that I can just, if I just suck it up and do what I need to do, it'll be okay.
Great, thank you. My second question would be, could you tell us one of the most tangible contributions that you have made in your career that had a direct impact on your life, professional or personal, and maybe on others' lives that you are most proud of?
Wow. Yeah, I mean, I guess to kind of break this into two categories, and one is on actual technical contributions I made with my mind or working closely with my students, and then our others are more on things I think that I've done that serve a broader community or maybe are different. And the first one, the answer is for me not so hard, because I spent like about 10 years working on a new area at the time called stochastic geometry that no one really seemed to appreciate or understand when I started working on it, but I could see that it was going to be important. And eventually I made a couple contributions, I think, to the communications field using that tool set that I think have stood the test of time and were fairly important. But I think maybe you're looking for a little softer answer. And I mean, I don't know how to give a really specific answer. I mean, I look, Ian touched a little bit on it in introducing me, but I'm really proud of my students. When I first started out as a professor, I was 28 years old, and I was often mistaken for a student myself. And so for many years, I really felt like an imposter, honestly, with this professor title in front of my name. And here I was working with students who were, in many cases, almost my age. They were late 20s. Some of my early PhD students were like Juan Choi, who's a professor now at Seoul National, was older than me. And so I think just working with these students and just treating them with respect and and just trying to just nurture them with my own curiosity and passion, and not really pretending like I knew everything, I think was an approach that worked well for me and for them. And I think that a lot of them have gone on to be wildly successful and really leaders, both in academia, and then also several that are working for major companies and have made really important contributions to LTE and 5G. And I guess, yeah, just they were, I don't know what the common thread was, but I think just that kind of curiosity and just really trying to understand things rather than just do things, just trying to look below the surface and understand. And I think that's it served them well in their career. And also I think I still have a good relationship with almost all of them because of that.
Great, thank you. And in which fields and topics you would recommend students to study today?
Yeah, well, I guess limiting this to my broadly speaking, the telecommunications area. Yeah, I think something we really failed at is providing global coverage. Particularly to the underconnected. It's very expensive to provide 5G coverage to rural areas or less developed areas. So I think things that bridge that gap are something that either bring down the cost radically of the terrestrial approaches, or these LEO approaches, which are being done by SpaceX and Amazon and others, I think are very exciting for the next topics for the next 10 to 20 years. I think obviously machine learning is interesting, and so I think this is machine learning obviously is a blowing up is a really perhaps overhyped area with attracting huge amounts of talent. But I think if you can learn machine learning along with communications or networking and understand both, there's not so many people that understand both, and you have to understand both to be able to do the kind of things that I was talking about in my talk today. So I think that's another good area. I think there's lots of interesting things as well, like some of the things Ian's working on, for example, in terahertz or in molecular and biological communication, also quite interesting. I just don't know as much about those.
All right. Could you tell us how will, in your opinion, generative AI like ChatGPT, the new Gemini, impact the future of research and also everyone's life in general?
Yeah, I mean, this is, I think, something we're all thinking about, whether you're a high school teacher or a college professor and researcher. I think we're all trying to figure this out and discuss it a lot. It's going to be very interesting to see how it all shakes out. I mean, obviously, it's a very powerful and disruptive tool, and and we're just probably at the beginning of what it can do. So I think students today need to learn how to use this tool, just like they learned how to use their scientific calculators and 40 years ago, and learned how to use MATLAB 20 years ago. Or it's a new tool that can increase an engineer's productivity. Certainly, I don't use it that much yet. But I think it's one of my on my list of kind of my homework assignments for when I have some free time, is playing with it more. It certainly can be used to write code, polish writing. So I'm still I'm still a really not very good at using it, but it does seem that it'll have an impact, and I hope we can just use it in a way that improves and amplifies innovation rather than stifling or replacing human ingenuity, because it doesn't seem like it will be that good at those things.
Okay, thanks. Actually, my last question now. I would like to ask you if there's a motto, an aphorism, a book, a movie, or a piece of art or music that describes you best that you would like to share with us before closing this webinar today.
Wow, that's
that's a very interesting question.
Ian, please join us. Turn on your camera.
I mean, I don't know. I don't know how to give that an answer to that one that doesn't sound intensely narcissistic.
Something you like?
Maybe can I maybe ask the question because this happens to me. So when you are sad, which music are you listening to? And when you are joyful, which music? For example, when I needed energy, I listened to techno music. When I want to be calm, I listen to the classical music, something like that. I don't know. Or
Yeah, that's actually true. I like a little known fact about me is I was a techno DJ in the 90s
Oh, all right.
for a few years. I was like kind of a very early in the like
It is very
race.
personal. Okay.
And so yeah, so I still like, that good electronic music definitely connects me with some part of my core, and I really, when it's done well, I really think it's still kind of fundamental and interesting. And so I guess, yeah, maybe I would say a song that I really connect with and maybe describe a little bit of my spirit is a song called Belfast. It's by Orbital.
yeah,
They're really techno artists, and it kind of gives a certain hopefulness and an arc of like joyfulness that I really relate to strongly.
true. Yeah, I heard this from another friend of mine. Yeah, true.
Ah, all right.
Yeah, the
Thank
techno
you.
was the best in the 90s. I still have those CDs, by the way. Anyhow, okay,
Thank
Alessia.
you. Thank you so much for being generous, for sharing personal advices and experiences and even music. Thanks to Ian, Ian Sport. So thank you. So Ian, we conclude our series for this year.
Yes, thank you, Alessia, and thanks a lot, Jeff. Really, it was a pleasure to listening to you and talking to you. And hopefully we'll see each other again somewhere, right? So the conferences are not attractive anymore, really. I don't go. It looks like you're also at home, right? You didn't go to GlobeCon.
Well,
So
I'll make an effort to reach out. Sounds like you move around more than me, so hopefully I can bump into you someplace you are, Ian. Real
I hope
pleasure.
so.
I
So
enjoyed
I
this.
hope we'll invite you to Abu Dhabi for one of these events.
That would be great. I would love to try to make that if I could.
Yeah, sure I
Thank
have.
you.
Okay.
Thank you again.
Thanks a
Thank
lot.
you,
And also
everybody.
thanks for the audience. We will continue next season, starting in January. We have again lined up many top scientists, so we look forward to launching another season. So thank you again. Wish you all happy holidays and a super 2024. Thank you.
Thank you.
All right.
Thank you, everybody.
Bye.
Bye-bye. Bye.
Thanks, Alicia. Thanks, Ian. Thanks, everyone.
Thank you. Thank you, Jen.